Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver a lecture on graph theory, lecture number 22, in which I will discuss on binary tree. Before defining binary tree, firstly, we define the rooted tree, as binary tree is also a rooted tree. So, we firstly define rooted tree, a tree in which one vertex is distinct from all other vertices, called rooted tree. The distinct vertex is called root of the tree. Here we see some rooted trees. Here V1 vertex is below the all vertices, and this vertex V1 is the root of this tree. And similarly, here also V1 be the root. In all trees, V1 be the root, and V1 has distinct identity, and all are trees. So these trees are all rooted trees. Now we define binary tree. A binary tree is defined as a tree in which there is exactly one vertex of degree 2, and each of remaining vertices of degree 1 or degree 3. Since the vertex of degree 2 is distinct from all other vertices, so this vertex acts as a root. So binary tree is a rooted tree in which one vertex is of degree 2 and remaining vertices are of degree 1 or degree 3, and this vertex V1 here in picture is of degree 2. This acts as a root of this tree. Here we see that degree of V1 is 2, degree of V2 is 1, degree of V3 is 3, and similarly we may see that except the vertex V1, degree of other vertices be either 1 or 3. This type of tree is called a binary tree. Now we prove a theorem. Theorem is number of vertices in a binary tree is always odd. Now we prove this. Let T be a binary tree in which number of vertices equal to n. Since in binary tree we have exactly one vertex of degree 2, and each of remaining vertices are of degree 1 or 3. Since 1 and 3 are odd numbers, therefore number of odd vertices equal to n minus 1. 1 be the even vertex, that is of degree 2. We know that binary tree is a graph, and each graph contains even number of odd vertices. Therefore, n minus 1 equal to 2m. M belongs to n. Here 2m is an even number and n minus 1 be the number of odd vertices in binary tree, that is in graph, implies that n equal to 2m plus 1. This is an odd number. And left side is number of vertices in binary tree, implies that number of vertices in binary tree equal to an odd number. Proved. Now we prove the next theorem. Next theorem is, if P be the number of pendant vertices in a binary tree and n be the total number of vertices in that binary tree, then P equal to n plus 1 by 2. Now we prove this. Let T be a binary tree n equal to total number of vertices, P equal to number of pendant vertices. Since binary tree contains exactly one vertex of degree 2, and each of remaining vertices be of degree 1 or degree 3. Since P be the number of pendant vertices, that means pendant vertices means the vertex with degree 1. So, number of vertices with degree 3 equal to total number of vertices minus number of pendant vertices plus number of vertex with degree 2. This equal to total number of vertices is n minus number of pendant vertices b p and number of vertex with degree 2 is 1. Let this is number 1. Since the vertex with degree 2 contribute degree 2 to the binary tree. P number of pendant vertices contribute degree P to the binary tree. The vertices of degree 3 contribute 3 multiply number of vertices of degree 3 equal to 3 multiply n minus p plus 1. Here number of vertices with degree 3. Therefore, total degree contributed by all vertices to the binary tree equal to 2 plus p plus 3 multiply n minus p plus 1. Let this is number 2, this is number 3, and this is number 4, and this is number 5. Since binary tree is a tree and it has a number of vertices, implies that it will contain n minus 1 number of edges. Since one edge gives rise 2 degree, therefore total sum of degree of binary tree equal to 2 multiply number of edges, means 2 multiply n minus 1. This is number 6. From 5 and 6 we get here in 5 2 plus p plus 3 n minus p plus 1, and in 6 2 n minus 1, implies that 2 plus p plus 3n minus 3p minus 3 equal to 2n minus 2, implies that here we get 2 plus 3n minus 3, this side minus 2n plus 2 equal to 3p minus p, implies that here 3n minus 2n, n, here 2 plus 2 4 minus 3 1, this equal to 2p, implies that p equal to n plus 1 by 2. Therefore, number of pendant vertices, p be the number of pendant vertices, equal to n plus 1 by 2. N be the total number of vertices in the binary tree. Proved. Now we define internal vertex. A non-pendant vertex in a tree is called an internal vertex. Pendant means the vertex with degree 1. Here in the figure we see that vertex of degree 1 be V1, V4 and V5. Therefore remaining vertices are V2 and V3. V2 and V3 are called internal vertices. Now we prove the next theorem. If P be the pendant vertices in a binary tree and N be the total number of vertices in that binary tree, then number of internal vertices in that binary tree is 1 less than the number of pendant vertices. Now we prove this. Prove. Let T be a binary tree N equal to total number of vertices in the binary tree, P equal to number of pendant vertices in binary tree T, Therefore, number of internal vertices equal to number of vertices in T minus number of pendant vertices in T. Equal to n minus p. This is number 1. Firstly, we find number of pendant vertices in terms of total vertices. From previous theorem, we get P equal to n plus 1 by 2. This is number 2. Therefore, total number of internal vertices equal to, here n minus p, we put the value of p here, n minus n plus 1 by 2, this is 2 n minus n minus 1 equal to n minus 1 by 2, this is number 3. Now, number of pendant vertices minus number of internal vertices equal to number of pendant vertices be n plus 1 by 2, number of internal vertices n minus 1 by 2. This is equal to n plus 1 minus n plus 1 by 2. This is 2 by 2 equal to 1. Therefore, number of pendant vertices minus 1 equal to number of internal vertices. Therefore, we may write this in left side and this in right side. Number of internal vertices equal to number of pendant vertices minus 1. Therefore, number of internal vertices in that binary tree is 1 less than number of pendant vertices. Here, number of internal vertices is 1 less than number of pendant vertices. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.